I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. The launching of the James Webb Space Telescope is one of the greatest human accomplishments. And here to explain why the Webb Telescope is such a big deal and how it will change astronomy is Silas Laycock, Professor of Astronomy at the University of Massachusetts-Lowell. Dr. Laycock is a specialist in distant galaxies, black holes, pulsars, and a number of other key areas of modern astronomy. His article in the online journal, The Conversation, about the Webb Space Telescope is an excellent public resource, and I think he'll refer to it in today's discussion. Dr. Laycock, welcome, and thank you very much for joining us.
Good morning, Yvonne. Thanks for the nice introduction and for inviting me on your program. Nice to be here.
Going to be fun. I've really been looking forward to this. First of all, about that project, can you give us a little background? Why is it such a huge accomplishment? It took so long. It's so spectacular. Could you tell us about it?
Sure. Well, in terms of taking so long, so the original proposal for the next generation space telescope, which ultimately became the James Webb Space Telescope, dates back to the 1990s. So I think it was originally proposed in about 1996, and it was originally conceived as an 8-meter telescope, similar to the giant telescopes that were then being deployed and built on the ground. And it went through several iterations. It was recognized by basically the whole astrophysics community that a big telescope with high angular resolution and sensitivity in the near and mid-infrared would probably be the most scientifically useful tool that astronomers could have. And that was the results of the Astronomy and Astrophysics Decadal Survey in 2000. So roughly every 10 years, the whole community gets together and says, what is the most interesting science? What kind of technology? What kind of observatories do we need? And it was at that point, around 2000, that this concept really caught fire, as it were. And so it went through a lot of planning and different concept studies. And at some point, it was decided to make it a little bit smaller so that it could be actually built and launched and get it into space without totally busting the budget. And so we ended up with this 6.5 meter telescope instead of 8, which is only a little smaller. And it took maybe 10 years from that point to get it fully constructed. And so I think construction was finished in about 2016 or something. And since then, it was being tested and on the ground and characterized, gotten ready for launch. I mean, the challenge of getting such a large telescope into space are just so many. I mean, you probably can imagine the cost of lifting something big and heavy into space is enormous. And so this telescope is been de-weighted, and it's made as lightweight as it possibly can. And so the biggest, the biggest and boldest decision, I think, in its construction was to, instead of sending up a single mirror, which can't be fit into the payload fairing of any rocket, had to be folded up. So it's 18 pieces. The 18 pieces had to be, unfolded like origami.
Right, like origami or something, right?
Exactly. So I think
it's amazing. The other thing is that this is deep into space, right? And we can't just go fix it like the Hubble. They
so
had to fix the Hubble, but they can't get to this.
So you'd asked me to talk about a little bit the sort of risks attached with this. And so the risk, obviously, of the origami structure is well known, I think. Some of the other risks are to do with its location, exactly. So in order to have this incredible sensitivity in the thermal infrared, which is basically where everyday objects glow, so the Earth, is glowing, you and I, our bodies are in the mid and near infrared. So if you want to have a telescope that's really sensitive at those wavelengths, it has to be super duper cold. And so it has to be far away from the Earth. And so that means it can't live in low Earth orbit like the Hubble Space Telescope does. So the Hubble telescope, flies over our heads about every 90 minutes, depending on where we are on the Earth, and it's at an altitude of maybe 300 miles or something. The Webb telescope is far, far, far beyond the orbit even of the Moon. It's 1.5 million kilometers away. It's about 3 times the average distance to the Moon, orbiting this special point called the L2 point, the Lagrange point. And this is a special place where, if we imagine this apple being the sun and my finger here being the Earth, and my thumb being the moon, the telescope is out here and it orbits in synchrony with the Earth. So as the Earth orbits the sun, the telescope stays out here, orbiting
Yeah.
around on the opposite side. And so as the telescope has its sun shield facing the sun to block all the light from the sun shield also blocks all the thermal radiation from the Earth and the moon. And then the telescope can look into the coldness of space in the other direction.
Yeah. Yeah.
And nobody can get there. With current technology, the telescope is not serviceable, but NASA did think ahead, and the Webb telescope is in fact being constructed to be serviceable. It actually has refillable propellant tanks. It has special markers on it so that in a future robotic mission, if it were ever possible, and if SpaceX or some company and successfully demonstrated it were feasible,
yeah,
the telescope could be refueled. It could be opened up, much like the Hubble was. The Hubble wasn't designed to be serviced in orbit so much, and so there were a lot of microscopic, very, very small assemblies that the astronauts had trouble with. So I think some thought went into the possibilities, even though we can't do it right now.
Right. And that's amazing that just the complexity of that thing, and then getting it into space and then opening it up. I think a lot of people, like I say, ordinary mortals, were just holding their breath. I certainly was at that time. It is really an amazing thing. Now, why is this such an advance over the Hubble? Because Hubble could look pretty far into space too, but it's shown again and again. The new images are really astoundingly different, clear. But can it look deeper into space than Hubble? And
yes, and for a few different reasons. So the most sort of obvious reason is that it's much bigger, right? So it's 6.5 meters diameter as opposed to 2.3 or something, whatever the Hubble is. So it's about 6 times bigger in collecting area. So it collects 6 times as much light, which just that alone would make it, much more sensitive. The way that optics and the physics of light and its interaction with matter works, the bigger you make your telescope, the finer the sharper the view that it can produce. It can focus the light of the star down to a much smaller spot. And so because of that, the Webb can focus the light into much sharper spots. So that means that it'll make things appear to be brighter if they're further away, just because it can focus whatever light there is onto a smaller area on the detector, so it will appear brighter. So the Webb's mirror has about 6 times the collecting area of the Hubble, so it sees much fainter objects. It also focuses light much more sharply by virtue of the way that optics works. So it's called the diffraction limit. So the diffraction limit for the JWST is much smaller, so it can focus more sharply. It can see more distant objects and see much more fine detail. And then thirdly, it being so far out into space with its sun shield. So Hubble does have some near-infrared instruments, WF3 and NICMOS, for example, but they are really severely hobbled by the fact that they're close to the Earth and they have this high infrared background. So being out in the cold of space with this special sun shield enables the cameras to be much more sensitive to much longer exposures, basically.
Okay. There's a couple of things that I would like to ask you to clarify for us on this, and one of these is the infrared, the redshift. All of that is really hard, I think, to understand. And I thought in the article you explained it nicely and so on. But so you're looking very deep into space, and you have explained, okay, that light has to travel a long distance, and something happens to it on the way. Could you please explain that a little bit? So we're looking into the very early universe.
Yeah.
The redshift, the infrared. Can you tell us a little more about that?
Exactly, yes. So this is one of the reasons why looking in the infrared was one of these high priority things for astrophysicists. And another of the reasons why the JWST can see further back into the early universe than the Hubble. So the universe is expanding, and it's expanding everywhere in some sort of uniform way, which means that the further you look into space, the further away, the faster the objects are receding from it. And so this leads to a phenomenon called redshift. And so if we look at the light of the sun, its spectrum peaks in the sort of middle of the visible part of the spectrum where we can see at a wavelength about 0.5 micron. Now, if you were to take a galaxy full of stars and move it to the far back in the early universe, such a galaxy would be receding from us at incredibly high speed, so fast that the light would be shifted from 0.5 micron out to perhaps a micron, which is beyond where our eyes can see it, into the infrared, and then further into maybe 2 microns, 5 microns, 10 microns, all the way out there. And so you need a telescope that can see the infrared light and focus it. And so the Hubble Space Telescope is limited by that phenomenon, redshift, to seeing to perhaps 400 million years after the Big Bang. Now, the JWST can see to much further redshift because it can see further into the infrared spectrum. So it can see galaxies whose light has been shifted all the way to the mid-infrared. And those galaxies are perhaps 180 million years after the Big Bang, which may not seem a lot given how old the universe is, but that transition in the early universe is the time when the first stars were starting to form and the first galaxies were being assembled. And so the difference between 400 million years and 180 million years is actually huge. That's the sort of region of the development of the universe that we've never seen before.
Right. And I'm going to come back to that because I think that's one of your things, especially I'd like to get into that a little more. One more of these sort of technical terms here. So there's the issue of the light, and this can capture that light way back. And that's a new thing. And the other is gravitational lensing. And there is that image from NASA. And I asked if you have it. If not, we'll insert it. But it shows that so well. What is it, and why do astronomers really like that?
Okay, so here's the image. So this is this is one of the well-known first light images, and it comprises of thousands of exposures. I think it's over 100.
That's great.
Of this this field in the universe. And so the size of this field is very small in some sense. It's about 2.5 arc-minutes across, which makes it much, much smaller than the full moon. But we can see that with the Webb's very, very fine resolution, we see a tremendous amount of detail in that small area. And so we see these bright things that are stars in the near universe with the 6 spikes. So those are the diffraction vanes of the telescope. And then we see many, many galaxies. And the galaxies are all different shapes and sizes and colors. And this field was specifically chosen because it is home to a galaxy cluster, which is a cluster of hundreds of galaxies, which are all very close together. And we see some of them in the image. In the middle where I'm moving my cursor, if you can see the cursor.
Yes.
Yeah, you see this big diffuse yellow galaxy.
Yes.
So this is one of the cluster galaxies. And this one is relatively close. It's at a distance of, I forget the exact distance. It's relatively close. It's not at some super distance. It's perhaps 4 billion light years away, which sounds very far away, but isn't that far away compared to the the dawn of time. Now, what that cluster is doing for us is it is bending the light of galaxies that are far, far, far in the background. So there's a phenomenon of gravitational lensing, which you alluded to. So photons, which are we think of light having a wave nature and a particle nature. If we think of light's particle nature, we think of light traveling as little packets of energy through space. And the path that they take, we think of light always traveling in a straight line. And it doesn't follow exactly a straight line. It follows the quickest path between any 2 points. Now, gravity bends the path of those photons much in the same way that a glass lens would bend the light of light, that's how optics work, how lenses work. And so this phenomenon of gravitational lensing. So we can imagine this big galaxy cluster that's sitting between us and the distant universe is bending the light from those distant objects. And we can see all these streaks and arcs that are kind of concentric. Yes. And so many of the lensed galaxies are very, very red in color. Now, very red, the way that this image was created at many, many different exposures at different wavelengths, and they were then stacked together to make this color image.
I see.
And the scientists who did that compositing made a choice about the colors so that red objects are really, really very, very strong infrared objects. And so these lensed arcs are they're smeared out because the lens isn't a perfect lens. So it wasn't a lens that was designed by people to be a telescope, right? It was just what nature provided. And there's some really interesting things. So this particular lensing arc here has 2 bright spots in it. And these are actually 2 separate images of the very same galaxy in the early universe. And this can actually be proven by looking at the details if one zooms in, which we can't really do here. But you can see that they're the same galaxy. Somebody with a spectrograph, so that Webb also can break the light up into its spectra. They have identical spectra. And there are many other of these pairs of lensed galaxies. I believe this is another pair over here.
Yes. So, yeah, that's very useful to you, I imagine, as astronomers. That really is helpful.
Yeah, it's useful for a lot of reasons. So one is it enables us to see those galaxies in the distant universe, and they become much brighter. So gravitational lensing makes the objects much brighter than they would otherwise be. It also provides information about the distribution of matter in the space between us and the distant objects. So astronomers are very interested in these other constituents of the universe. You know, we have all the stars that we can see, we have the gas that we can see, we can have gas that we can see with radio waves and X-rays and so forth. But you know, we think that there is all this other matter out there. And dark matter is the name given to this material, which
Yes.
appears to be responsible for gravitational lensing on these large scales. And so the distribution of dark matter, a lot could be learned about it by these kind of measurements of gravitational lensing. Now, there's another image that goes along with this one that probably hasn't received quite as much airplay. If I zoom down, they provided the same field,
Yeah.
so there on the right is the
Yes.
near-infrared image.
Yes.
On the left is the image from the mid-infrared instrument, which is seeing the longest wavelength.
Yeah.
And if you compare them, you notice that many of the galaxies and stars are not really visible in the mid-infrared at all.
Right.
Some of them are really strong. And so this lensed galaxy here and some of these other ones that I was pointing out. So those are galaxies where really all of their emission has been shifted far, far into the infrared. And so those are, you know, galaxies that are way, way back at the very, very high redshift universe. And so, for example, those are the kinds of galaxies that scientists could not see at all previously because we couldn't access that redshift range very well.
So this is really opening up a lot of the universe to you astronomers now, right?
Yeah, absolutely.
Do you expect that there's going to be a lot of revision in astronomy or a lot of questions answered that you couldn't get answered before?
Well, I really hope the answer to both of them is yes. You know, it would be terrible if you know the human race had devoted this huge amount of resources and time of these thousands of people and billions of taxpayers' dollars, and we didn't discover things that we never expected or never knew before.
Yeah.
But I think a lot of the headlines that are coming out and being discussed on social media about exactly this very thing, that's exactly what the hope really was, that we would see things that were not expected, and that the telescope would provide information that was beyond our current capability to understand it with the models that we have now, and that we're seeing that is the case.
So this will clarify a lot of things for astronomers to have this kind of close identification like this. It must be quite amazing. And is this, by the way, the mid-infrared instrument that you mentioned, the MIRI, is that new with the Webb?
It is, yes. So there have been other space satellite infrared astronomy missions. So the ISO, the International Solar Infrared Observatory, the Europeans flew in, I think, in the early 90s, and then the Spitzer Space Telescope that NASA flew in the early 2000s. So the mid-infrared range has been accessed before from space telescopes, but those telescopes all have very, very small apertures, and so they were not able to deliver high angular resolution views like the Webb telescope delivers. And so they provided a very kind of blurry picture of the distant universe, and they were really very good for looking at much closer objects.
Yes, I understand. This we just have like 5 minutes or so left, so I want to get a couple more things in here if possible. You mentioned something called transit spectroscopy, and that this will be very important for like reading atmospheres. And I have another question about that too. Can you tell us what that is also?
Yes. So I don't know. I have this on a piece of paper, but you can get this image from NASA. It's on their website. So transit spectroscopy is the idea of looking at a star that has a planet around it, and the planet will go in front of the star and block the light out. However, the transit is never complete because planets tend to be small compared to the stars that they're orbiting. So the planet will only ever block a tiny piece of the light from the star. Now, some tiny fraction of the light from the star will pass through the atmosphere of the planet in a very similar way to on the Earth. We sometimes have lunar eclipses where at night we see moon going a strange copper or red color, right? Because the light that is reaching the moon during a lunar eclipse is light that has filtered through the Earth's atmosphere. And so, in principle, if you were an alien sitting on the moon, at that time, you could study all about the constituents of the Earth's atmosphere. You'd probably be able to discover that we had chlorophyll and chemistry in our atmosphere that was, indicative of life and all kinds of exciting things. So transit spectroscopy is the idea of trying to do that same thing, capture light as passed from a star through the atmosphere of a planet and then analyze that light and use it to understand the chemistry of the planet's atmosphere.
So it will give you a real leg up on understanding these atmospheres, these remote atmospheres too. And on that, there have been several reports just in this week that people may be misreading these things. And I thought at first when I saw the first one, I think it was in Nature or something, I thought, wouldn't you expect some misreading at the very beginning? Doesn't it take some time to adjust these very sophisticated technologies? And are people really leaping to conclusions, reading atmospheres as they are right now?
So I went and read those articles that you had suggested, and it's very interesting. I think it's a perfect example of what you were asking about in your previous point. Will the Webb show us things that we didn't expect? And that this is exactly what's happening here. People have spent the last few years building models about what we expect to get for planetary atmosphere spectroscopy. And it's been attempted with other telescopes on the ground. So the Gemini telescope that I was associated with in the past has done a lot of work on transit spectroscopy, but the difficulties of working through the atmosphere have meant that the data has been very, very limited in its quality, its spectral resolution, its sensitivity, and so forth. And so the models have, I think, also been at that kind of level. They've been models that have been built to interpret the kind of data that we had available to us. And suddenly we get these amazing transit spectra from JWST, and they really have so much more detail that the models that we have are not capable of correctly, perhaps, understanding them. And so this article that was in Nature went into, if you fit the models that we have to the new data, you could in principle get some answers that might be biased or wrong because the model's not quite capable of capturing the level of detail actually present in the spectra. So it's fuel for the theorists to go back to the drawing board and incorporate, more physics in their models.
Right. But as an astronomer and very experienced with this, you couldn't be too surprised that it would be a little rough at the beginning, I'd imagine, right?
No, not at all. I mean, the same is the case with the observations of the distant universe. We expected that we'll see the galaxies from the very early universe, but it's an open question as to what it will look like. Exactly at what redshift will they appear, exactly how much structure will they have, and at what redshift range. And there are many, many theories being published in papers about what we think and what we know, and those are going to be revised, and they're going to be wrong, basically. Right. That's what we built the telescope for.
Yeah, well, and it's important for the public to understand too that people in science, you do revise things. As you learn things, you change things as there. But it was funny to see like 3 articles right in a row. Oh my gosh, people are jumping to conclusions here. But I don't think it just didn't sound logical. Scientists expect to have to revise what they think they have at the time, and planets are tiny compared to galaxies. So, Dr. Laycock, before we leave, I would like to ask what you are most interested in. How will this benefit your research? What is the most exciting thing for you?
Yeah, so my research is on something called X-ray binaries, which are mostly black holes and neutron stars in orbit with other stars. One of my students actually had this nice paper this week about some work that we've been doing, building models of gravitational lensing in systems where a black hole and a star are orbiting one another. So this picture comes from an article that was published about that work. And so it looks very similar to an exoplanet transit in some ways. And so it turns out that the same kind of abilities that JWST has that were designed to look for exoplanet transits could also be used to look for black hole transits and neutron star transits in close binary systems. And so we'll be able to study how the black hole lenses the light from the background star. And in principle, this is a way to discover many of the black holes that are probably hiding in the universe. and measure their masses and all sorts of other exciting things. So there are another dimension of what JWST does, which is interesting for my work. So here, this is a concept of an X-ray binary. So an X-ray binary with an accretion disk feeding its companion star. These disks that form in many binary systems radiate very strongly in the infrared. And so it would be very interesting to have this capability to see infrared circumstellar disks and accretion disks in detail. And then thirdly, the X-ray binaries that we study, many of them are in galaxies that are awash with gas and dust that makes them opaque at optical wavelengths. And so many of the studies that we've done over the years have shown that the center of our own galaxy contains thousands upon thousands of X-ray binaries, black holes floating around in the center of the galaxy. And it's been very, very difficult to study them in detail because we can't pierce through the veil of dust that shrouds the view. And so having a telescope that can do that with high angular resolution is something we've really been waiting for probably half of my career. I'm very excited to start writing the proposal to use the telescope to do this work.
You feel like it has your name on it here.
I hope so.
It's going to answer a lot of questions for you. I imagine this must be a tremendous thing for a lot of people in astronomy today, because it'll just open up some, answer a lot of questions that you have. And I look forward to hearing more about this. This is early days, and it's still very exciting. Dr. Laycock, I'm afraid we have to end, but I hope that we get a chance to talk to you more about your work specifically in the future, because you're doing a lot of things that are of great interest that I guess that the Webb will be able to address, that will be able to be helpful to you in that regard. So I thank you so much for joining us today, and this was most interesting.
Thank you for having me on. It's always a pleasure to talk about astronomy to the public.